In this part, I'm going to continue my discussion on scaling. As the first example, I'm focused on insect size. The size of insects are about a few centimeters. However, there are movies such as Jurassic World, which there are huge, giant insects. Have you ever seen such insects in real world? Are there any physical constraint on the size of insects? In fact, here we want to focus on these type of questions. Physical constraint on the size of insects. Our approach is based on breathing. Insects do not have lung. They cannot breathe like us. So they typically get the required oxygen through their skin. As a model, let's consider the shape of an insect to be a sphere of radius r. Then its surface is proportional to r to the power 2, and its volume is proportional to r to the power 3. As r scales by 2, s scales by a factor of 4, and v scales by a factor of 8, and the ratio of surface to the volume scales by 1/2. Then the area of its skin becomes 4 times larger. So it can absorb more oxygen, up to 4 times more. But on the other hand, as the volume scales by a factor of 8, the number of their cells increases by the same factor, means 8. Then its body needs more oxygen, 8 times more oxygen. So when the insect size doubles, it gains at most half of the required oxygen. This may be the reason why we do not see such giant insects now. What we are talking about are spherical insects, like bees. If the insect is very long, such as dragonfly, the above model does not work anymore. Larger insects are elongated ones. Currently, 20% of the air is oxygen. If a higher percentage of air was oxygen, probably there exists more insects, more bigger insects. There are theories that million years ago, when a large part of the earth was covered with dense forest, the percentage of oxygen was higher than now. There may have been larger insects at that time. The second example, but with the same physics, is food absorption. Suppose creatures absorb food through their skins. If these creatures are alpha times larger, their body surface scales by alpha square, and their volume scaled by alpha to the power 3. As a result, when these creatures grow, their surface to body ratio decreases by the factor 1 over alpha. That means the larger the creature, the smaller the nutrients that each cell can absorb. If the absorption of food in the human body is performed in a spherical region, we would probably face a deficiency of the absorbed substance. This problem is solved in the human body by long tubular intestines, which is in this shape. In this way, the surface that absorbs the nutrients is enlarged. In addition, the internal walls of intestines are not smooth, but they have millions of intestinal villi. These villi cause a much higher level of contact in the intestines. All these make more absorption of food. The final example is heat production versus heat loss. Let's compare a bear and a rat at the North Pole. Heat production depends on the number of cells, so it scales with volume, which is proportional to r to the power 3. But heat loss is proportional to the surface, so it's proportional to r to the power 2. Thus, the ratio of energy dissipation to the produced energy is scaled by the inverse of the length, r inverse. For example, let's compare a mouse and a bear. The mouse weighs about 100 grams and bear weighs about 600 kilograms. Assuming both almost have the same density, we can obtain the ratio of their volumes. And if we compute this to the power 1/3, this is the ratio of their size, length size, which is about 6,000 to the power 1/3, which is about 20. So the energy loss of the mouse is about 20 times larger than that of a bear. As a result, life at the North Pole is much harder for a mouse than a bear. Of course, this is not the only parameter. Other control parameters, such as finding food, are also important. There are a set of parameters that determines which creature can survive.